Hi everyone, thank you for your patience. I would now like to hand over to Brian, who will be your MC for the webinar. Thank you.
Hello, this is Brian Benson at DamWatch. Got with me David Menendez, and actually David's going to lead us through the bulk of the presentation, but I'll join us towards the back end when we get to the Q&A and discussion of the learning opportunities. Take it from here, David.
Okay, well, good afternoon. Thanks for joining us. My name is David Menendez, and today we're going to be talking about lessons to be learned from the Oroville Dam incident. This is a joint presentation by me and by Brian Benson. We both work from DamWatch, a consultant specialized in dam engineering and dam safety.
Can I please just invite you to pop your camera on? Thank you.
Yeah, we found that. Thanks.
Okay. So I will briefly go over today's agenda. We will start by briefly describing the Oroville incident and explain why we chose it for today's presentation. Then we will discuss what happened, describe the mistakes and failures that led to this incident, and then talk about some of the lessons that we can draw from this event. We then have set some time aside for discussing learning opportunities with the group and what practice we keep, stop, and start based on the lessons from the Oroville incident. The entire presentation will last around 45 minutes, so please post any questions or comments and we will go through them in our discussion section. And if you can, start identifying lessons that can be applied to your current practice so that then we can share them with the wider group towards the end of the seminar. For those of you that don't know, Oroville Dam is the tallest dam in the USA with a maximum height of approximately 235 meters. Its main functions are water supply, hydroelectric generation, and flood control. The project was completed in 1968. So at the time of the incident, which was 2017, it was nearly 50 years old. The incident that we will talk about today is the failure of the chute of the Oroville Dam main spillway due to excessive uplift induced by the flow. And it happened on February 7, 2017. Today, we have decided to emphasize some of the human factors that led to the incident. In particular, we are going to be talking about the decision to close the spillway gates after the chute failed, which is what led to a critical situation that on February 12 led to an evacuation order for almost 190,000 people that were living downstream of the dam. Thankfully, this order was lifted 2 days later and no uncontrolled release of the reservoir took place. So, just 1 second. Yeah, just briefly, I want to touch on why we think that it's an interesting case for all civil engineers. Well, first of all, many spillways built before and even after Oroville were built sharing many of its design features that led to the chute failure. So this incident is leading to a revision of the safety of many spillways around the world. Oroville has also contributed to a shift in how we conduct safety reviews. Since we will see that one of the main lessons is the need to focus on an analysis of the structure with respect to current practice and first principles, instead of simply basing our opinion on past performance trends. We also believe that Oroville is a good example of the age-old disconnect that many times occurs even today between geologists and engineering geologists and design engineers. Finally, many of the problems and mistakes that took place in Oroville could have been prevented, and many are rooted on human failure, as I said earlier. So the lessons from this incident are applicable to all engineering disciplines, especially when it comes to complex projects like Oroville Dam. So this is a bird's eye view of Oroville Dam, and I have marked the main structures that we are going to be discussing today. The embankment dam is in red, and the powerhouse is at the foot of the dam. The main service spillway should fail is separate from the main dam, and it's on the right abutment. And this is a short emergency spillway that had never operated in the 50-year history of the dam. So before we start talking about what happened, I wanted to mention that most of what we're going to be discussing today is based on the report by the independent forensic team that was convened to determine the causes of the incident. This was a requirement by the Federal Energy Regulatory Commission to the owner of the dam, which is the California Department of Water Resources, or DWR. It's a very good document and one of the main references on this incident, and we will mention it again later. As an initial comment, the surface spillway chute was founded on rock of varying quality, and in particularly, it crossed an area of very weathered rock and residual soils. And even though this was clearly recognized by the geologists during construction and accurately mapped, the engineers did not alter the design of the chute that assumed good rock. In January of February of 2011, the spillway had its first significant discharges in almost 6 years. When the chute failed, the spillway was discharging approximately 1,300 cubic meters per second. However, in the morning of February 7, DWR staff that was monitoring the dam noticed a disturbance in the spillway flow. After closing the gates, they noticed that an entire section of the chute slabs was missing. The slabs had been lifted or undermined by the flow, and erosion of the foundation beneath the slabs had started. The independent forensic team determined that the most likely cause of the failure was uplift due to stagnation pressures forming on an offset into the flow on the spillway surface. This is a process where water is injected into the drainage system through open joints or cracks in the slabs, and the Oroville spillway chute was particularly susceptible to this failure mechanism due to the fact that cracks had formed along the entire chute aligned with the drainage system pipes since the time of construction due to a failure in the design that we are going to mention later on. In the following days, the DWR opened the gate several times to test the progress of the damage, since they had hydrological models that predicted increasing inflow into Lake Oroville, and they expected that they were going to need to operate the service spillway. When they operated the spillway, erosion progressed, but did not really continue to upstream to affect the upper chute. However, there were two potential problems that threatened the operation of the dam. First, the debris from the foundation erosion were being deposited on the river, and they started raising the tailwater levels. This threatened to flood the powerhouse, and furthermore, if the erosion of the chute progressed upstream, it could affect a transmission line that crossed the spillway, and these were serious concerns for the people in charge of the emergency, because it was believed at the time, even though it was later disproven, that if any of those two things happened, the powerhouse would not be able to operate for several months. We're going to look at some photos now. This photo shows the condition of the spillway chute after the spillway gates were first closed. And you can see the missing slabs and the erosion progressing behind the left sidewall. This is an interesting photo of an inspection in the area eroded while the gates are closed, and you can see the weathered and fractured rock where the chute was founded, and the relatively thin slab used in the design for those that are used to seeing modern spillway chutes founded on weathered rock. Here's a photo of the river near the discharge point of the services spillway. In this photo, the spillway is in operation and the erosion had progressed significantly from the first photo. and it's forming an alternate channel. The debris on the river that you see are the ones responsible for raising the tailwater levels. And finally, here's a photo of the erosion close to the transmission tower. Despite how close the erosion was to the tower in that photo, it finally never undermined the structure. So continuing the tale, what happened, as rain continued and the reservoir rose, the moment that I mentioned came to happen. The people in charge of the emergency had to decide between two courses of action: opening the spillway gates of the service spillway and lowering the reservoir, and perhaps flooding the powerhouse or destroying the transmission tower, or close them and let the lake level rise. This would cause water to flow over the emergency spillway, which, as I mentioned, had never been used before. The emergency spillway is a concrete weir that discharges onto the natural hillside. It was never lined in concrete because the opinion of the engineers reviewing the dam since the time of construction was that the rock was sound and no significant erosion was going to take place, even in the case that the emergency spillway had to operate. But however, like in view of what had happened to the service spillway and having very quickly reviewed all the available information on the geotechnical characteristics of the rock in the area, there was a strong recommendation from the civil and geotechnical engineers not to use the emergency spillway. Unfortunately, operational concerns ruled the day and the emergency spillway started to spill. Very quickly, the erosion was very significant and started to progress towards the weir. And if the weir was undermined and it fell, it could cause the uncontrolled release of part, not the total, but part of the reservoir volume down to the emergency spillway foundation level. With the head cutting approach in the foundation of the emergency spillway, the evacuation order was finally issued in the afternoon of February 12th. So this is a photo of the emergency spillway operating. And here you can see the erosion progressing towards the emergency spillway. The topography kind of concentrated the flow, the discharge from the emergency spillway into a channel. So next, we are going to be watching a short video of the dam on the day that the evacuation order was issued. So just 1 second. This is the service spillway operating. You can see the alternate channel for the discharge. On the sidewalls, you see the drainage system discharging into the chute, and this is the channel that was formed by the discharge from the emergency spillway. You can see how all the discharge was concentrated on a channel. Later that same day, you can see the erosion progressing towards the emergency spillway. That was a critical situation that led to the evacuation order. You can see how close it got to the foundation. So there's no apron or no dissipation structure at the foot of the emergency spillway. After this situation took place, the service spillway gates were open, and until the entire time until the flood passed, the lake level was lowered and the emergency spillway stopped operating. And thankfully, the erosion in the service spillway did not progress upstream towards the gates. So the emergency passed, and 2 days later, the evacuation order was lifted. So these are some of the main mistakes that we decided were worth emphasizing today. First of all, it is worth noting that the design did not meet the best practices of its time and was not adjusted, as I mentioned, to the real site conditions found during construction. Current chute slabs incorporate a series of design details, especially when they're founded on poor foundation, like in this case, that serve as defensive features to prevent this type of failure. And some of them are water stop, shear keys, reinforcement, crossing the joints, and some other. And some of these were not in the Oroville chute design. For instance, it didn't have water stops. Since construction, there have been many inspections and safety reviews, and yet these vulnerabilities had not been recognized. The foundation rock was in general estimated to be of very good quality, and erosion was not expected to be significant, even in the unlikely case of a situation like the one that took place. Many vulnerabilities now recognized in the design and many signs of anomalous behavior have been normalized through the years. The chute had cracked almost immediately after construction along the under drainage system because the drainage pipes had been installed protruding into the chute, into the chute slab, and reducing the thickness of the slab. And this was not a typical design of its time. The high drainage flows were cause of concern at first, but then it was later accepted as normal. There were also several chute slab repair projects during the year, and the independent forensic team found that they were mostly ineffectual and even harmful to the chute. That was caused, in their opinion, by the DWR and consultants that worked on them not understanding the underlying causes for the problems in the spillway chute. There were also many human errors listed in the AFT report. Most of them were centered on the owner, DWR. In general, the forensic team found that the DWR was overconfident and complacent regarding the risk to the structure. First of all, there was a widespread belief that the quality of the work done during the design and construction of Oroville was beyond reproach, the best of the best during its time. There was also less attention paid to pertinent structures like the spillway versus the embankment dam and the powerhouse. And finally, the DWR didn't have any experience managing major incidents with a dam portfolio. Some of the comments that are common to most dam owners is that they have a reactive approach to managing their civil infrastructure, mainly due to cost control pressures from many sources. Also, as commonly happens in many dams, many times operational concerns such as water delivery or power production reign over dam safety issues. And finally, the forensic team believed that the dam owner relied heavily on regulators, consultants, and the regulatory processes. Typical safety reviews that follow the standards set by regulators might not be enough to successfully address the safety needs of critical infrastructure like Oroville Dam. And also, as the third point brings up, even though the technical capacity of regulators in the USA is very high, the resources that they can assign to an individual dam are generally limited and probably not sufficient for Oroville. An interesting point is that they also observed that poor information management could have contributed to the fact that several review teams didn't recognize the significant hazard to the spillway chute. Because relevant information was not easy to access, in particular documents from the original design and construction, and this is also very common with found in old dams. Another comment from the forensic team was the generally insufficient technical expertise in dam engineering and dam safety of the DWR staff, and even in some of the external consultants in charge of reviews. One point that I found very interesting was that they mentioned that they did not find records of a specialist in spillway design in particular, having reviewed the service spillway during the entire 50-year period since construction. The final mistake that we listed was a lack of emergency scenario training. This is also common among dam owners throughout the world. Furthermore, most training is usually geared towards scenarios that could result in a breach of the dam and the release of the entire reservoir. Partial failure cases like the one that we discussed today are usually overlooked. In fact, the 190,000 people that were evacuated were chosen based on the inundation maps corresponding to a breach of the whole embankment dam. And the failure of the emergency spillway would likely have affected a much smaller area, but those inundation maps were not available. So next, I'm going to pass the presentation to Brian, who's going to be talking about the lessons that we can get from this incident.
Sure. So the independent forensic team, literally a who's who of the best dam safety and dam engineers in North America. And they really put a great deal of emphasis on the human and organizational factors that led to the incident and the lessons to be learned from the human and organizational considerations. And we're just going to boil down a handful of the main lessons that we thought were applicable broadly across engineering practice. And this top one here, I consider, one of the old golden rules that past performance is the best predictor of future performance. But in fact, I mean, what we know, but we commonly many times don't recognize is that change is always occurring. And the challenge is identifying what that change is and how it can affect our structures over the long term. Particularly when there's not an extreme event that triggers us to go look beforehand. It's common, just like this instance, we dissect it thoroughly after an extreme event. And this second one on this slide relates to what David's touched on, but which is really worth emphasizing, and that there's this human nature tendency to normalize past behavior, even though it may be abnormal relative to what we consider good performance. And this is, I say here, can be waiting for disaster to strike. We'll see, there's this incident with the condominium in Florida still ongoing at the moment. Ongoing the rescue and recovery, but no doubt there'll be another forensic investigation of that. We don't know what they're going to say, but I have a sense we'll get some relation to this human factor in that instance as well. And then a couple more lessons pertain to human and organizational factors, and this is organizational bias towards what's immediately in front of you, and those tend to be operational issues over long-term, typically safety concerns. Until inevitably, if you ignore those long-term concerns too long, it's too late. And then finally, this last one, the bottom of the slide, that these lessons tend to repeat over time. In fact, in Oroville, I don't think there's any quote unquote new lessons, even the spillway specific kind of technical takeaways, and especially the human and organizational lessons. These aren't new, but the independent forensic team points out and states strongly that they are still to be learned by the engineering profession. So, coming at things, our engineering with fresh eyes and minds is important to help potentially try to break any cycle of bias that exists. Holly, we can't advance. Oh, there we go. Okay, so this brings us to the discussion part of the presentation, and I think the first thing up here is addressing any specific questions from the participants to the presentation.
We have one question from Natasha Middleton, and it was she's asking what was the size of the flood in terms of average exceedance probability or return period. I don't know exactly what the return period was, but it wasn't close to being the maximum flood that the spillway had passed. Had discharged like 3 times more flow in the past, I think. But the design, no, sorry, I'm exaggerating. It's like, I think it was twice as much in the past for the peak discharge. But the design flow for the spillway was 4,500 cubic meters per second, I think. So this was a relatively high discharge, but nowhere near the design flood. In fact, for this type of failure mechanism, sometimes the situation is worse in the cases of lower discharges because the weight of the water on top of the slab is less, smaller, because your depth is smaller, but the velocity of the flow, which is what drives the stagnation pressures that generate the uplift, don't change so much. So they're very close to the one that you'd have for the design flood. So usually these are the cases that drive this type of failure mode. I will try to look it up during the discussion to see if I can find the actual return period.
Yeah. Here's a question. Was there no consideration given to the impacts of emergency spillway spilling in the design or safety reviews? Wasn't it designed to spill water? Yep, and this is, it was, but I think there's a great deal of hope sometimes associated with these emergency spillways. My own experience, even in New Zealand, particularly in New Zealand, this also holds true in some cases. So they're designed to spill very infrequently. The issue at Oroville was really the assessment, the erodibility of the geologic materials. And in the original design, there was a gap between the engineering geologist who raised a red flag about this and the design engineers who, well, I don't know if they overlooked it or didn't appreciate it, but there's enormous pressure typically in large complex construction projects to press on. So definitely there were decisions made to press on. And then this was part of the normalization that this was just accepted over time. And I mean, in one way, it was successful in that the dam didn't fail. And that is the fundamentals behind the design, but there was definitely an underappreciation of the erodibility of the materials. Anything to add on that, David?
I think that's good. I mean, there was the report talks about a myth about the quality of that rock. Like everyone had a very good idea that it was very sound rock and it was not going to erode quickly. I think that was accepted by many reviewers without actually maybe going back to the basic data from the construction time, and that was raised as one of the mistakes.
Mm-hmm. Here's one about emergency spillway. Was it adequately sized? Is there anything in the report about that? In your review, David?
No, as I said, I don't know what the capacity of the emergency spillway and the services spillway are with respect to the PMF, which would be probably the appropriate design criteria nowadays. But I do know that when it was repaired, the capacity was not increased. The section was stayed the same, and considering that they basically rebuilt the entire structure, I assume that that would have been an opportunity to increase the capacity. This was not a problem of capacity, though. Like there was much more capacity in the services spillway that was needed for that event. But the emergency spillway is typically not expected to operate except for much more extreme floods, right?
Oh, here's one for me. How do we overcome the geologist-engineer barrier? This seems to have been a basic problem here. Oh, not just here. I've been practicing engineering since 1983, and that is one of the fundamental issues in civil engineering, I can say, that happens over and over again. I have a somewhat unique perspective on it. My undergraduate degree is in geological engineering, which is a blend of engineering, geology, and civil engineering, particularly geotechnical. And the root cause, I mean, it's one of basic communication and just organization. In my view, we need the engineering geologist involved throughout the project, not just at the early planning and early design stages. They typically on big projects come in very early and then during construction. But that gap in between, I think, in my view, it would be good to keep them involved through the whole process. And yeah.
We probably need to maybe 5 more minutes of questions.
Yeah.
We've
got.
Do any other questions that you think? Were there any signs of distress other than directly after the construction to the spillway previously? I mean, yes, the signs were there throughout the entire 50-year history. There was significant cracking along those pipes that I mentioned throughout the entire chute. That thing that they observed after construction, that the discharges from the drainage system were very high as soon as you open the gates, was something that was known. I think what was not expected was that this could lead to a sudden failure. Like, even though the failure mechanism is known, it wasn't expected to be likely. And again, even in the case that it happened, there was a lot of trust in the quality of the rock to prevent the erosion from reaching the control section, which in a way that was actually that did happen. The erosion never progressed upstream towards the control section. But yet, I mean, there were clear signs, and that's why the report mentions that those vulnerabilities were not addressed. There's also another comment on any specific on the concrete lining joints with respect to increasing the hydraulic uplift condition. Yes, there's something very interesting in the report that you can look at. That is, the forensic team asked the regulators to do a statistical analysis of the features in the joints of spillway chutes of that time, basically, I think from 1950 to 1978, and compare that to what was done for Oroville Dam. And they found, that in some cases Oroville was typical of its time, and in some others it wasn't. Water stops were not nearly as common on those joints as they are today. Only, I think, 1/3 of all the spillways had them. Oroville did not have them. That wouldn't have helped along the cracks, though, so that probably wouldn't have. We don't know whether the failure was induced at a joint or at a crack, but if it happened at a crack, the water stop wouldn't have helped. The main feature that was not in other spillway was that drainage pipe protruding into the slab and reducing the thickness and basically inducing that crack. That was something that they only found. The drain within the slab was something only found in, I think, in 8% of all cases. So there were other features, but I don't think we have the time to go into the detail. But the report has a lot of information on that.
Okay, I'll take all the easy ones. What is the current situation at Oroville Dam? Has the spillway been repaired and improved to take future large floods? Yes, it has. Yeah, and they did it quite, they got onto it quite quickly because, there was another flood season around the corner. It is a multi-billion-dollar repair. It's worth taking a couple minutes to look at some of the photos on the California DWR website, just to appreciate the scale, if nothing else. There's a really nice photo I saw of the service spillway flip bucket splitter blocks, and each block is bigger than your average house. It's pretty impressive.
Yeah, and the protection on the new emergency spillway, there's a large apron now that they built, stepped very long with a cutoff at the end. So I think many other things are more likely to fail than the emergency spillway now in Oroville Dam. So there's actually a photo in the presentation if you go back to lessons of the new spillway. But yeah, some other.
Was there any independent review of the original spillway design?
At the time of the construction, right? At the original design. Well, there's no records. The report mentions that it's something that is also interesting is that despite that idea that it was done by the best of the best, apparently the design was done by a relatively inexperienced engineer, a recent graduate, and it's not known how well it was reviewed internally, even though it was the spillway of the tallest dam in the USA, right? Which is something unexpected, but that's something that is in the report. And at the time of construction, there's no known review of that design that was listed in the report.
Here's one for you, David. Would you typically install a leakage detection system under the spillway as an alert?
Well, I mean, the drainage system was a great leakage detection system, right? Because it was dry before they opened the gates. They opened the gates, the water started flowing on the chute, and then there was a lot of water coming out of them. And that was an atypical, as I mentioned, like an atypical condition that is not seen on dams typically. And that was a clear indication that the water was coming from the flow conveyed by the chute. So I think that was understood. I don't know if it was understood by everyone, but there was a clear idea that was the reason. It's just that maybe there was no clear sense of the hazard implied by that condition.
Yeah, but there are spillways like a lot of existing spillways that don't have under drainage, and to monitor uplift pressures, we go in and put in piezometers occasionally, right?
Yeah.
Yeah, excellent.
But it's not typical for such a high discharge going into the under drain system. That's not usually how you design them.
Yeah. And here's a question. Didn't fail, but how close was it to failing with the erosion from the emergency spillway?
It was very close.
Well, if I was the dam safety engineer standing on top of the dam, I would be extremely uncomfortable. Would have been, yeah, definitely. Yeah, I mean, that the backward head cutting, I mean, was uncomfortably close to the concrete weir of the emergency spillway, in my view, definitely. What would have happened? Well, I mean, you would have had uncontrolled release. How deep, how bad it would have been there, I mean, would have depended on, you know, the quality of the rock as it down cut. But yeah, it would have been bad.
I think we're running out of time and we have to go to the keep stop start.
Oh, that's right.
Yes.
I think we better move on.
Yes, we're really sorry that we couldn't answer all the questions, but
That's most of
we
it.
had to finish the presentation.
Yeah. So, okay, so just know that this independent forensic team report's out there. And you see, I made a note there that if you can even just read the executive summary, that would be amazing. It's very insightful. And if you want a PhD dissertation type coverage of the human and organizational factors, read the Appendix J of the report. You can find the report easily online. Just Google it or go to damsafety.org. Right. So let's just take a moment to consider, self-reflect, and think about for a moment what you might keep, stop, and start from our presentation of the Oroville incident as applied to your own engineering practice. So, and I had a little trouble, to be honest, thinking of it in this way, so I modified that a little bit, and I just said, how might these lessons shift what I'm doing in my own practice? So if you have anything to share about that, put it in the chat. But to keep things moving, I'll share a little bit of myself. So for me, based on the Oroville incident learnings, I think I'm going to keep thinking critically with an independent mindset using first principles, not blindly accepting past precedent and other, definitely in my earlier career, other experts' opinion that from preeminent experts. I know in my own experience, they're not always right. So that's keep, stop. For me, I think, what did I say here? I think I'm going to stop assuming past acceptable performance will necessarily continue. I mean, that's a pretty straightforward one. And of course, that's not a new learning, but I constantly got to remind myself about that one. And starting on reflection, I thought I'd start considering potential major incident events, including serviceability events related to dams, in addition to potential failure events. And this is something I know the dams industry is in the process of upgrading our thinking, and it is another of the lessons from Oroville as well. That because we're generally focused just on failure, because that's the standard of practice. We got to prevent failure. But these major incidents can have enormous consequences, both to the public, but especially to the owners, regulators, and other stakeholders. So if you have anything to add with what you might keep, stop, and start, we encourage you to share if you so like.
Holly's telling us that if we have time, we can finish and answer the rest of the questions.
Yeah, okay.
So
Yeah, we still have about 10 minutes left you've done the wrap up. So I wonder if perhaps we could go back to the questions. There are a few more on there. If you're happy to do that, we can maybe tick some more off.
sure.
Great.
Okay, so was anyone prosecuted or held liable?
I honestly don't know the answer to that.
I don't know either, but I don't think so. I haven't heard of anyone being prosecuted for this.
No, I don't either.
But I cannot say for sure.
As far as I mean, to my knowledge, there were no deaths directly related to the incident.
Right.
Yeah. Sorry, can't shed any more light on that.
Tim Gilliam.
Yeah, that's a good one. In the New Zealand context regarding emergency spillways, do you think there should be more detailed guidance in testing emergency spillways associated with dams? Note, obviously hard to generate a flood event, but perhaps generation could be paused, service spillway gates closed, and flows diverted to emergency spillway. Well, I think this just brings up the broader issue of design flood passage. And I think in the past, there's been a tendency to just, we need more flood capacity, we'll just stick an emergency or an auxiliary spillway over to one side of the dam or somewhere else in the reservoir. And that's kind of it. But over the last number of decades, floods have tended only flood passage requirements have only tended to increase, and who knows what's going to happen in the future. But if we're going to be incorporating climate change in many places, those requirements are only going to increase. So, any thoughts about that?
Yeah, I mean,
question?
Unfortunately, some emergency spillways cannot be tested. For instance, if you have a fuse plug, you'd have to make it fail in order to test the emergency spillway. So it's very difficult. And also, usually in an emergency spillway, you accept a certain level of damage because it will only happen for very improbable cases, right? You might need that capacity for the PMF, for the 1 in 10,000, 1 in 50,000 average exceedance probability case. So it's widely accepted to that some damage is okay, but if you test it, you have to repair that damage afterwards, right? So I think it's very, very difficult to test them. I think you basically have to have very robust, reliable designs, and use that as your control of any potential consequences.
Yeah. I know. It's in some cases in New Zealand, the emergency spillways now have probably. Well, there's cases where the frequency is just too frequent, and they should only be used, designed to operate quite infrequently.
Yeah. Leon Rodriguez says, did the design engineers mention why they chose to ignore the geologists? I don't think, there's no record of them purposefully ignoring the geologist and the geological information. It might have happened, but there's no record and no mention in the report of that. Historically, what's happened is that there was a divide in the information that was created by the geologists and the engineering geologists, and the one that was used by the design, because that requires someone modifying the design based on the understanding the information given by the geologists, and then understanding what needs to be modified in the design based on that, and that's the disconnect. That's someone that bridges that gap. Yeah. So that, I mean, I doubt that they did it on purpose. But
yeah,
I don't know. Do you wanna?
I can, not at Oroville, but I have firsthand knowledge of a case where an engineering geologist, same in a dam the same age as Oroville, drew an issue about poor geology and was overridden by the chief engineer because of schedule and cost, but mostly schedule requirements. The show must go on. And I'm sure that's happened in more than that particular case. So that's definitely one cause.
Jirishi's question, I think we already answered. The spill has been repaired. We did talk about that, right, Brian?
Yeah.
So the new design is way more robust. I think we answered Fred Clark. Michael Mifflin, do you want to? So it says, with the lesson of human and organizational lessons tend to repeat over time, what measures or organizational changes were undertaken? Also, with outside fresh eyes and minds to break a cycle of bias, is this perhaps including a schedule of external audits from experts?
Yeah, sure. I don't have firsthand knowledge of what DWR, the owner of Oroville Dam, has actually implemented. I'm sure there's others that do. But the audits, yes, in the dams industry, we do that, right? We have in New Zealand for dams that can cause major and large and severe consequences. Every 5 years, an expert or a team of experts, as appropriate, has to review the safety of the dam, and that is considered a dam safety audit, and it's pretty extensive. But that's exactly what happened at Oroville. But there is a higher level of review, and it's more of a detailed design review, and those are very unusual in New Zealand. But that's been mentioned as a consideration for the future.
Just to wrap up, some people actually send their start, keep, stop comments.
Oh, yeah, lovely.
So maybe we can close on that.
Yeah, go ahead.
So Jared says start is doing emergency scenario training.
That's good.
Brian Mercer says keep learning and always look to develop more. Stop assuming it will work and current practices are appropriate. Start thinking about being self-responsible for design and inputs into a project. That's good. And I don't know if Natasha's is also part of that keep, stop, start, but she says, we have certainly seen that mindset at play. We haven't done it, tested it before, why do it now? Operationally, attitudes, assumptions, and actions can be driven by a fear of not knowing what might happen if something is tested.
Yeah, I mean, in dams, we have this mindset that commissioning is never complete because there can always be a bigger event, a bigger flood, a bigger earthquake. So precedent events is something to keep in mind, I think.
So I think we have to wrap up. The time is over.
Yeah.
Can we go back to the presentation? So anything else that you?
No, that's it. We're very thankful for everybody who participated in the presentation and for Engineering New Zealand, and especially Holly for helping us with it. We hope you got something useful you can take into your own practice from our presentation of the Oroville spillway incident. Thank you very much.
Thank you.
And an extended thanks to the both of you for taking the time to share it all. We've got some great comments coming through saying it's really interesting, they've really enjoyed it. So if anyone would like to see the recording, we'll be sharing that on the Engineering New Zealand website under the Lessons to be Learnt tab. You will see all the previous sessions on there as well. But once again, thank you both for taking the time out, and I hope you both have enjoy the rest of your day.
Thank you
Thank
very
you.
much. Bye now.